Welcome everyone to the webinar. My name's Stephen Cole. I'm going to introduce the Altair product EDEM and outline what is DEM. So as an overview of some of the topics that I'm going to discuss, I'll look at the differences between the continuum and the discrete method. I'll also talk a bit about the background of the discrete element method and some of the key components of the DEM, as well as the CPU and the GPU solvers. In addition, I'll talk about some particle shape representation and end with a note on material calibration. This is one of the key topics of the discrete element method. So here's a few examples of EDEM applications. We can look at storage and conveying of materials and also mixing. The two cases here, for example, are powder-related simulations. We can investigate material separation, including sorting and breakage using different methods and methodologies. And also with heavy equipment, we could look at soil, tool, ground interaction. With ground-like materials, we can look at the interaction, look at vehicles, for example, soil, tire interactions as well. Spreading and distribution of materials is also an application case that we can investigate. In this simulation, we have a rotating blade distributing materials, and the investigation is the spatial distribution of the granular material. So what is DEM? Discrete element method is a way of simulating discrete matter. DEM is one of the most popular methods for making use of this methodology. It can be precisely defined as a particle scale numerical method for modeling the bulk behavior of granular materials, as well as materials such as coals, ores, rocks, aggregates, pellets, tablets, and powders. It can also capture the dual nature of the fluid-like material and the solid. In EDEM, we calculate the particle displacements and rotations and also detect the contacts with an assembly of particles. When it comes to simulating particulate systems, there are two main modeling approaches which could be used, the continuum and the discrete method. In the continuum approach, shown here on the left, the behavior of the granular material is described by constitutive laws. These laws are commonly expressed in the form of differential equations, and they relate to mechanical field variables like stress and strain. Modeling a substance as a continuum completely fills the space it occupies. As a result, the behavior of the individual particles is ignored, and the resulting equations are solved, and this is a method similar to finite element method. In the discrete approach used in EDEM, we're modeling every individual particle as a distinct entity, and we represent the granular material as an idealized assembly of particles or shape. The overall system behavior results from the individual particle behavior, so this is the DEM method. Just to visualize the differences between the two methods, here we see a blade pushing through a bed of material and how it would be represented in the two different methodologies. In the discrete method, we can see the individual particles in this case. And really the method as a whole gives us the advantage of modeling discontinuous granular flow, and also includes different physics such as cohesion and plastic modeling of materials. The history of DEM dates back to the 1950s or 1960s, when the theory of discrete element modeling was introduced for the purposes of molecular dynamic studies, which is a movement of interactions of atoms. The principles of the discrete element method were then developed in the 1970s. The two approaches are quite similar. However, molecular dynamics is focused on molecules and atoms, Whereas with EDEM and discrete element method, we're really looking at larger scale granular materials, powders, rocks, iron ore, agricultural materials, and so on. So why use the discrete approach? First of all, many systems, many particle systems behavior is highly dependent on the particle level behavior. And in EDEM, we're simulating the behavior of all the particles individually. So we can really track each individual particle and the forces and the velocities of these within a system. Secondly, with the discrete model, we can accurately model the interactions between the granular materials through the different contact models, which I'll go into later. This can lead to a wide range of different behaviors, such as cohesive materials. So let's have a look at the DEM methodology. This flowchart gives us an overview of the calculation cycle in EDEM. First off, we typically would detect contacts, something which I'll go through later in the presentation. From the contacts, we calculate the forces using the physics models. From the forces, we calculate the accelerations, and using Newton's laws of motion, the velocities and the positions are then updated using numerical integration. After updating the particle positions, the algorithm then searches for new contacts, and the whole cycle repeats, and we repeat this every time step. The diagram here on the right shows how the normal overlap is defined for two colliding spheres. It's simply the sum of the radii minus the distance between the centers. As the particles initially move together, we have an overlap, and from that overlap we calculate a force and the particles move apart. The image is for normal overlap. There's a tangential component, a sliding component, which is slightly more complicated but has the same principle of overlap resulting in force. For this case here, we have a simple three-particle system, which would be very easy to solve in EDEM. However, calculating the resultant positions of these three particles might be quite difficult to do as a hand calculation. So at the beginning, we've actually set up a case where we have no gravity and the particles have an initial rotation and linear velocity. As they move closer to one another, there's no forces acting on them. So the velocities stay constant at each time step, and then eventually the particles collide. From the collision, we can see a change in the velocities and the positions. And it's when the particles collide we get the overlap. The normal and tangential forces are calculated on the particles from this overlap. And this calculation happens every time step. From the overlap, we get the resultant forces and the moments, and using Newton's laws, we obtain the accelerations, and through the numerical integration, we update the particle positions. The time step calculation is critical to EDEM simulations. It has to be small enough to ensure numerical stability and accuracy, and large enough to allow for reasonable simulation time. The stability and accuracy is achieved by preventing excessive overlaps between particles. You can see in the image here we have a very large overlap. One way of approximating a suitable time in EDEM is to calculate the Rayleigh wave speed, which is used to calculate the Rayleigh time step. In a real-life assembly of material, the force transmission between particles, between elements, is calculated through a Rayleigh wave which travels on the surface of a body. There's a time at which this force acts, and the critical time period is called the Rayleigh time step. It's important maybe to clarify that the Rayleigh wave is not simulated directly in EDEM. It's just a method we use to calculate the time step in EDEM. So we can see there's a few key components to the equation: the particle radius, the density, the shear modulus, and the Poisson's ratio of the particle all go into the calculation. The time step is then calculated in EDEM. There's an auto time step option which automatically sets it to 20% of the Rayleigh time step. 20% is typically a good approach, and the user can also customize this to any value they wish. Overall, this leads to a relatively large number of iterations within the simulation because the time step is typically quite small. And here's an example of 6 simulations run at different time step values. We can see on the bottom right here the simulation is unstable. It's running at 100% of the Rayleigh time step, and the 80% is also unstable. 10, 20, 40, and 60 for the moment is stable, but this one will also eventually show some instabilities, some explosions. So the simulation stability really depends on the parameters. Higher velocities and forces typically require a lower time step, and we recommend 20% generally. As I mentioned earlier, the particle forces are calculated through a contact model, and the real-world deformations is modeled as an overlap, which is used to calculate the force. In this animation, we can just see the kind of force time or force overlap component. As the particles move together, the overlap increases, the force increases, and as they move apart, the overlap decreases and the force decreases. So what is a contact model? I've mentioned this a few times. The contact model is a model which calculates a force when the particles are in contact, and generally speaking, not always, the force is based on the overlap. And the overlap results in forces and moments, which gives us the final velocities. There's a range of different contact models available. We have 2 types, elastic and plastic. And within these groups, you can have cohesive and non-cohesive behavior. This gives us a range of base models that we can represent different materials. For cohesive elastic materials, we use the JKR model. For dry granular materials, elastic, we'd use Hertz-Mendelin. For plastic, non-cohesive materials, you might want to use a hysteretic spring. And the Edinburgh Elastoplastic Adhesion model, the EPA model, can actually be used to model all the different scenarios, but it's the only model which can represent elastic, cohesive materials. And I'll give an example of this in the video here. We're running the same simulation with the different models. We have a starting point, and we'll compress the material down, and we can see in the plastic models the plastic behavior of the material. It doesn't bounce back to its original starting point. Now we're lifting up the cylinder. We can see the cohesive nature of the EPA and the JKR models, and the more free-flowing behavior of the hysteretic spring and the Hertz-Mendelin models in this case. So the different models can be used to represent the different material types and the range of different behaviors you see by all the various materials. Another important aspect of DEM is contact detection. This process is really very computationally expensive, and together with the force calculation takes around 80% of the DEM computational effort. This is because it involves continuous checking of the distances between elements in the simulation. And if you have thousands or millions of elements, then there's a lot of checking to do. This can typically be a grid or a bounding volume hierarchy search method. If we look at the grid method, we can have a simplified case here and split the domain into cells. The cell size is usually determined by the user. EDEM will identify the active cells, then identify the particles that are in contact within the active cells only, so it's really restricted the search down to a smaller area. We then calculate the forces, update the particle positions based on the forces. We'll reposition the elements, recalculate the grid. The optimal grid size is typically 3 times the smallest particle radius in the simulation. There's a secondary search method, which is a BVH, bounding volume method, in which case we'll divide the volume into bounding volumes. Initially we have 1 volume, and maybe we want to split it into 2 equal volumes. And then further into multiple volumes for different areas, and this creates a tree-like structure for each case. And we can search through each branch of the tree simultaneously if you have a multi-CPU, multi-GPU simulation, detect contacts, and it really speeds up the contact detection method. So the grid approach is typically used in CPU calculations, and the user will specify the grid size. The BVH model is typically used in GPU simulations and is automatically calculating the bounding volumes each time period. So I've introduced the 2 solver types, the CPU and the GPU. For the CPU, we typically see AMD or Intel CPUs, and these can vary from 1 core to 40 cores. It's limited only by the hardware available for a shared memory system. So it's shared memory only, not distributed on CPU. With regard to GPU, we can run on NVIDIA or AMD GPUs for OpenCL, but only NVIDIA supports the programming language CUDA. The OpenCL solver is slightly older, and the CUDA GPU solver is the latest solver and has benefits in terms of memory and speed. It's the choice going forwards for future development is NVIDIA at GPU processing. So here's a graph of a few simulations, each run with 1 million particles. It's scaled so that 12 CPUs is representing a value of 1, and the rest of the graphs are scaled based on this. The OpenCL solver provides approximately 10 times speed up in a lot of the cases, whereas the latest CUDA solver provides 25 to even 30 times faster than the 12 CPUs. CPU is always double precision, and the CUDA solver could be a mix between double and single precision, which is a hybrid, or it could be a single precision solver. You can see the hybrid is faster than the double. Moving on, I'd just like to present a few different ways of modeling shape in EDEM. Spheres are the simplest shape to model. However, we don't get any interlocking. A perfect sphere really will rotate very easily. We use spheres typically for pharmaceutical powders, where the shape of the powder maybe is irrelevant, and the cohesive and the semi-static nature of the material really prevents rotation. There's different physics models suitable for this. So a simple computational element like a sphere is very well applicable. The multisphere shape is generally approximated by multiple overlapping or touching spheres whose centers are fixed relative to each other. The advantage of this method is that we get an approximation of an irregular shape while maintaining the computational efficiency and accuracy of the spheres. For polyhedral particle shapes, this is defined in terms of corners and edges and faces. The advantage of the polyhedral is that it can accurately represent these flat and sharp edges, which we'll never really get in the sphere method. We can also represent spherocylinder shapes. This is really very similar to the multisphere method. It's spheres with spherical ends connected by a cylinder. When would we want to use a polyhedral shape over a multisphere shape or vice versa? This depends on the real material that you're modeling and the computational effort. If we compare this 12-sphere particle with this 64 triangle diamond, we can see that the diamond is 1.6 times more computationally intensive in this middle case. However, if our real material is a kind of sharp-edged shape, then the polyhedral particle would be the better case to really represent those sharp edges. If it's a more kind of rounded, rock-like material, a multisphere shape, even typically we find 3 spheres is an optimal type of shape. See that adding in more triangles increases the computational effort, and it's also always worthwhile bearing in mind that the shape is a representation of the real material, but every individual particle is going to be different. So we just want to create a representation of the real shape, and then we need to look at material calibration, regardless of the methodology and the shape used within our simulation. So within EDEM, we want to calibrate simulation results against known experimental data. The topic of calibration is a webinar in itself, but just really to highlight, there's a series of calibration kits in EDEM. These are a collection of standardized tests and associated analysis scripts which allow you to automate a lot of the calibration workflow. The calibration kit removes the need to model the standardized tests, which reduces the amount of engineering time required to calibrate a material model. It just allows you to use the software for design purposes. So within the calibration kit, we have a dynamic angle of repose test, FT4 rheometer, inclined plane test for particle equipment interaction testing, different types of shear cell, static angle of repose test, or angle of repose test good for quite dynamic systems, uniaxial compression test. And in EDEM 2022, there's a new cone penetrometer test designed for soils and material calibration when looking at off-highway vehicles. In addition to the material calibration tests, the series of already calibrated materials within the software calibration kits for powders and rock-like materials as well are available. So thank you for listening, and I hope you found the overview and the What is DEM webinar interesting.